Welcome back. So let's now discuss the PCA algorithm steps. So suppose we have x1, x2, x3, x4 and so on until we reach xm, right? And each of these x's are actually n-dimensional vectors. So basically if we have x capital, right, or all x's together, we will have an n times m matrix. Okay, so the n is the number of dimensions or the number of features, the number of variables. You can call it whatever, okay? So n is the number of dimensions. For each example, right, for each example, we have n dimensions, we have n features, and we have how many samples or how many examples? We have m samples, okay? So that's why we have x1, x2, x3, so each x is corresponding to a specific example or one example. Okay, now what we are going to do, the first step for the PCA, is that we are going to compute the mean, the data mean. So how we calculate the mean? We just sum all the variables, right, sum all the examples, and then divide by the number of examples. Okay, so let's say we have 2, then 3, then 1, then 4. So we sum all this together from 1 to m, and then we divide by the number of examples we have. And then we will have x dash, just like this. And the second step, after computing the mean, the global mean of the data, we will subtract the mean from each row of x. So this is basically called, we are centering the data. And you can revise this part in the statistics and probability sections of the course. Okay, so we are centering the data, and we will call the data after centering phi. So each phi will correspond to the original example after subtracting the mean of the data, right? So we compute the data mean once, and then we subtract the mean for each row, okay? And the third step is that we will basically form the matrix A. So the matrix A is basically phi 1, phi 2, phi 3, phi 4, and so on. So it's the same matrix we had before, the n times m matrix, after subtracting the mean. So the same data after subtracting the mean or centering the data. And from this matrix, we can compute the covariance matrix. And you can also revise this part in the statistics section. So we will compute the covariance matrix. How we can compute the covariance matrix? We will multiply each example, right, by its transpose. So for each example, we will transpose this example, right? We have a vector, right? We have a vector, some examples like this. We have a row. If we transpose this row, we will have a column, right? So we will multiply each element in the row by its respective element in the column. So we will multiply the first row by the first column, the second row by the second column, the third row by the third column, and so on. Or if we have it in a matrix formation, then we will just write A times A transpose. So if we multiply a matrix by its transpose, we will have the covariance matrix. So what will be the shape of the covariance matrix? If you remember, or if you know anything about linear algebra, then you know that if we multiply a matrix by another matrix, we need to have the number of columns of the first matrix equal to the number of rows of the second matrix, right? So if we have n times m, we need to have here m times something, right? And the output matrix will be this dimension, right, times the second dimension of the second matrix. So if you multiply n times m by m times n, because this is the shape after transposing, then we will have the final output n times n, right? So the final covariance matrix will be n times n, right? And you can, as I said, check the statistics section and you will find the discussion about the covariance matrix there. And from the covariance matrix, we can calculate something called the eigenvalues. And this is a very famous linear algebra concept, okay? And we call these eigenvalues lambdas. So we have lambda 1, lambda 2. How many lambdas? We have n lambdas. So we have an eigenvalue for each column, right? For each column, we have an eigenvalue. So we have n columns, so we will have n eigenvalues. So if you check this video, I will leave it in the resources. So if you check this video, it's talking about how we can find the principal components, right? So it's talking about the mathematics behind finding the principal components. So we'll basically find the eigenvalues by solving the determinant of sigma. So sigma is C, the covariance matrix. So, and we will know right now what do we mean exactly by the determinant, right? So we will have the covariance matrix, and we will subtract from the covariance matrix lambda times I. So what is I? I is basically an identity matrix. So the identity matrix is a matrix that has 0 everywhere and 1 on the diagonal. So diagonal will be 1s, 1, 1, 1, 1, and any other stuff or any other values in this matrix is basically 0. Okay, so if we multiply this identity matrix, we call it identity matrix because if we multiply it by anything, then the output will be this thing, right? So if we multiply lambda by the identity matrix, we will have the identity matrix. Okay, so we will compute the determinant of sigma or C, the covariance matrix. We have some values. We will subtract lambda times I times the identity matrix. So as we said, we will have 0, right? 0 everywhere and only values, some values at the diagonal or on the diagonal, right? So that's why here, as you can see, 2 minus lambda, right? And here we have 0.8 but not minus lambda, right? So we will have minus lambda on the diagonal, and we will have the values of the covariance matrix everywhere else, right? And from here we can compute something called the determinant, right? And we will equate this with 0, right? So as you will see here, you will see that here what we are doing is that we are basically computing the determinant. So the determinant is basically this term times this term minus this times this, right? So this term times this term minus this term times this term. Okay, so we'll have an equation equal to 0. So we can solve this equation on the calculator. It's very, very simple. So we'll have lambda 1 and lambda 2. So we have 2 columns, so that's why we have 2 lambdas, right? And this is the values of the lambdas. This is how we compute the eigenvalues. I will leave this video in the resources. You can check it, and it's not only one video, it's a series of videos for the mathematics, talking about the mathematics behind PCA, right? But we are not really interested in all this. I just wanted to give you like a refresh for your linear algebra, but if you are not familiar with linear algebra, this will not be a problem at all. You just need to know the concept of the eigenvalues. And from the eigenvalues, we can compute something called the eigenvectors. So basically, eigenvectors are computed using the eigenvalues. Okay, so we'll have u1, u2, u3 until we reach un, right? So for each eigenvalue, we can compute the eigenvector. And since C is symmetric, so what do we mean exactly by symmetric? We mean we have a square matrix, right? N times n, and let's say the value number 1, 2. So the index 1, 2 is equal to the value 2, 1, right? So this is what do we mean exactly by symmetric. So if you look at the triangle right here in the covariance matrix, you will see that it's equal to the triangle right here in the covariance matrix. So this is what we mean by a symmetric matrix. So since C is symmetric, we have a theorem in linear algebra that says that if a matrix is symmetric, then the eigenvectors of this matrix form a basis. So what do we mean exactly by a basis? It basically means for any example can be a linear combination of the eigenvectors. So if you remember, theta I or phi I, right? If you remember, phi I was the example after subtracting the mean, right? So we can say that we can reconstruct this phi I, this example, using a linear combination of the eigenvectors, right? So we have u1, u2, u3, u4, and so on. But we don't have b's, right? B's are basically the weights for each vector, right? For each eigenvector. So using some mathematics, you will find that B is basically equal to U transpose, U is the basis matrix or the eigenvectors, right? And phi is our examples, right? So if we put our examples all in one matrix and we put U in one matrix and transpose it, then we can compute B. So basically we can say that the principal components are equal to the eigenvectors. So when we say eigenvectors, we mean the principal components, right? Because here we have the first principal component, the second principal component, the third principal component, and so on. So this is the first principal component, this is the second principal component, and this is the third principal component, and so on. So this is the same idea of the eigenvectors. So if you want to know more details why we say principal components are equal to the eigenvectors, I will leave this video in the resources and you can check it, right? So you can check the covariance vectors and you can see principal components equal to the eigenvectors. So you can check this video and you will know all the details. Okay, now the 6 steps. Now after this step we will do the dimensionality reduction step, because right now we have how many features, how many principles? We have n principal components. So we didn't really do any dimensionality reduction because we had in the beginning n dimensions. So we had n features and now we have n principal components, right? Now for the dimensionality reduction step, we will keep only the terms corresponding to the k largest eigenvalues. So again, what we are going to do is that we are going to compute the eigenvalues from the covariance matrix, and this covariance matrix is coming from subtracting the mean from each row, and we will get these eigenvalues. They will be values, right? They will be 0.1, 0.2, 3, 4, whatever, right? So we will sort them in descending order. So the first one will be the largest eigenvalue and we will get the corresponding eigenvector. So this will correspond to the largest eigenvalue and so on and so forth, right? So for the dimensionality reduction step, we will keep only the terms corresponding to the k largest eigenvalues. So we will sum from 1 to k instead of from 1 to n. So we will keep b1, b2 and b3, for example, if k is 3. So the dimensionality reduction step will be really helpful if we have, let's say, 100 dimensions and we want to keep only 3 dimensions. So we will keep the largest 3 eigenvalues, right? So this is basically how it works. This is the main steps of the algorithm. So as you can see, we are now doing this step called the covariance matrix. We can do it in another way called the SVD. So there is a problem with these computations, which we will discuss in the next lesson. So we will discuss what is the problem, mathematical problem in all this, and then we will understand the difference between covariance matrix and singular value decomposition and how they map to each other. So let's go to the next lesson.